Assalamualaikum and a very good morning. Okay, so we have discussed this earlier from the previous video for filter circuit realization of filter circuit design. So the first step would be to calculate the filter order number n, in which you need to make sure it is just a whole number. Okay, so a whole integer. So you don't have to consider the point. If you have the point number, then you need to round it up to the next higher whole number. Okay, so you can calculate the n, the filter order number, either by using the equations, if you have the equations in hand, or by referring to the attenuation versus the normalized stop band frequency graph. Okay, if you are using the equation, please don't forget to consider the omega Sn is the normalized stop band frequency. So omega Sn, for example, for low pass filter is equal to omega S over omega P in radian per second. Omega S is the stop band frequency, while the omega P is the pass band frequency. And the alpha S, Max, and also the alpha P is the pass band, stop band, and also the attenuation factor or ripple factor, all in dB. So you just need to include in the value in dB. For example, if the stop band gain equal to 30 dB or the attenuation is minus 30 dB, so you just need to consider 30. Okay, you don't have to convert it into dB into linear values, and you don't have to consider the positive or negative sign. Alright, next, once you have the n, the filter order number, you will come up with the normalized low pass filter circuit realization. So you will be referring to a table. So either the maximally flat or Chebyshev filter, depending on the ripple factor for Chebyshev. So you'll get the low pass filter circuit realization. Okay, next, the third step. From second step, you have the normalized circuit in low pass filter mode. So if the designer or the system needs other types of filter, for example, high pass filter, band pass filter, or band stop filter, or even the low pass filter itself, from step 2, you need to perform filter transformation, in which the normalized circuit in step 2 will be converted or will be transformed to the final or actual circuit designed by frequency and also component transformation. Okay, so that's scaling and also in the component values and also in terms of the frequency. So that's equation that you need to consider in the transformation. Okay, lastly is the implementation. If there's lump element or planar element to be implemented at the end. Okay, let's look at this example. So this is basically the example that we have seen in the previous video. So in previous one, we have calculated the n by using both the equation and also the graph, attenuation versus the normalized stop band frequency graph. So just a quick recap on this example. So in this video, we are going to proceed with the normalized circuit realization and also the actual circuit transformation. All right, so the design of a Butterworth low pass filter. So it is this is maximally flat types of filter with the cutoff frequency 11.25, the pass band gain and stop band characteristics are given. So if you have this kind of statement, it will be good if you can convert this into or illustrate this by using a filter response. So it is a Butterworth flat top low pass filter, flat top low pass filter, and the omega C always at minus 30 dB, sorry, minus 3 dB point attenuation, Okay, this is 0 dB. Okay, and then this is your omega C equal to 11.25 radian per second. Okay, a passband gained in between 1 to, and so in dB it is minus 1 dB, so it's here. So this is your alpha P. Passband gain is minus 1, and also your omega P from 0 to 10 in omega radian per second. Okay, and then you have your stop band gain of minus 30 for omega of 20. So here is your omega S equal to 20, and the gain is minus 30. Okay, so from the graph you can actually get all the informations. Okay. Okay, so as discussed earlier, once you have the end, the filter, or once you have the information, then you need, the first step is to determine the end. So you can use either the equation. So this is the Butterworth, so make sure you use the Butterworth equation if you have the equation in hand, or else you may refer to the graph. So omega Sn here again is the normalized stop band frequency, in which from the graph at the bottom, the x-axis represents the omega Sn. Okay, so for low pass filter, the omega Sn from the equation is omega S over omega P, or from the graph it is equal to omega S over omega C minus 1. So omega here represents the omega S, and this equation is only valid for low pass filter. For other types of filter, so there will be a different equation of omega Sn. Okay, so from the graph, the omega Sn here is equal to 0.77. Okay, somewhere here, and the stop band gain is equal to 30. So the cross section is there, so it is around between 5 to 6. So choose the larger n, okay, the higher n order number. So in this case, the n equal to 6. Okay, so once you have the n, so the next step is to get the normalized secured components. So in this case, we have discussed this earlier as well. So for n equal to 6, so you can choose either the first, the second, or the third configuration. So commonly we are using the first and the third one. So for example, I've chosen the first configuration with the C component in parallel. So if you look at the table and compare with the end, when n equal to 6, the number of inductor and capacitor combination will be up to 6, okay, up to G6. All right, and G7 usually is basically the terminated load, okay, or the load resistance, right? And the normalized value will be always equal to 1. All right, so in this case, for the first configuration, so the first component is C1. So the value will be from the table, the first column is G1, right? C1, G1. So you can put the values in 0.5176, followed by the second one, the series, in series, so 1.4142, followed by the third component, and then the fourth component, and the fifth component. Okay, the fifth 1.4142, here is 1.4142, and lastly the sixth component, in this case the inductor, so it is 1.5176, terminated by the load resistance, normalized load resistance. So this is your normalized circuit. Okay, once you have the normalized circuit, okay, as from the previous slides. So now you need to transform the normalized circuit into the actual circuit. So from the question asks you to design a Butterworth low pass filter, meaning that the circuit is in low pass filter mode. Okay, from the second step, you always come up with the low pass filter circuit normalization. Right, so for final circuit normalization, you will convert this normalized circuit into the actual or the real low pass filter. So you need to refer to the filter transformation table. So look at what happened to each of these components in the normalized circuit for the actual circuit, right? So for low pass filter, and it's still in low pass filter, but the value of the component will be modified or be changed based on the equations, okay, and the orientation of the components, right? For example, the first one, so the R here and here is maintained, but then both are the normalized value, so Z divided by Z naught. So if your Z naught equal to 50, so you got the normalized value equal to 1, so the Z here equal to 50 as well. Okay, divided by 50. Right, so in this case, C1, the first component C1 is in parallel. Okay, so this one is in parallel. So refer to the parallel one. So the C will maintain as it is still C in the actual circuit, but the value will be modified. Okay, the actual value will be calculated by using this transformation equation, right? So in this case, C divided by Z naught, 50. So omega C from the question is 11.25. So C is the normalized value, the current normalized value. I would say it's C, maybe CK. K representing the element number. Okay, all right. So then followed by the second one. So L in series. So L in series, what happened to L in series? So in series, the L will be as it is, still inductor, but the value will be modified, okay, by using the new equation. So let's look at how to transform this. So the final circuit, so C maintained as it is. Oops. Okay, C maintained as it is, but the new C1 will be calculated by using this equation. C, the current C, C1 divided by Z naught 50, omega C is 11.25. Alright, so then the second component, the inductor from normalized circuit become in series, so it's still inductor. And what happened to the value? The inductor L2 is equal to, so for inductor in series, it's Z naught divided by omega C L. So L is the current normalized value, so 1.4142 multiplied with 50 divided by 11.25. So repeat all the steps up to the final components in the circuit. So then you'll get your final or actual circuit. Good. Let's move on to what happened to from the step 2 normalized circuit, low pass filter circuit, if you have to design other types of filter. Okay, for example, high pass filter, band pass filter, or band stop filter. Right, next, if you have to design low pass filter to high pass filter, then you have to consider the omega n for high pass filter. Okay, and if you have band pass filter or band stop filter to be designed, so the omega n will be equal to this equation, and this is the fractional bandwidth equation. It is omega 2, the passband frequency, so omega 2 omega p2 minus omega p1 divided by the center frequency, omega naught, right? So okay, if you have to design the high pass filter, so the normalized stop band frequency is equal to minus omega c, the cutoff frequency, divided by omega s, stop band frequency, minus 1. So from the graph, if it is a Butterworth filter, high pass filter, Butterworth high pass filter, so at the bottom is omega Sn equal to this. So the omega Sn can be calculated by using minus omega c over omega s minus 1. This is for high pass filter. Okay, if you have the band pass filter or band stop filter, then omega Sn can be calculated by using this equation. Alright, so please make sure you alert with this equation. Okay, alright, then once you have the omega Sn value, then the stop band attenuation in dB, then you can project the lines from x-axis to y-axis, then you'll get your n. Alright, and then okay, for the second step, this is for the first step, so you get the n value. Okay, to get the filter normalized filter circuit, once you have the n, refer to the normalized filters circuit realization table, then you'll get the component configuration. Right, then in the third step, to get the actual circuit, so you need to refer to, for example, to design a high pass filter, so you need to look at what happened to the step 2 circuit, normalized circuit. For example, if you have this series, the inductor in series, so to get the high pass filter, the inductor will be transformed as a capacitor in the actual circuit, and the new value, the actual value, can be calculated by using the equation shown. Alright, so because from the step 2, if you alert in step 2, you always produce normalized low pass filter. Then to get other types of filter as the final circuit, so you need to transform the low pass filter in the second step into the required type of filter. Right, for example, you are required to design a band stop filter. So proceed the first step, find the n, and then proceed with the second step to design to get the normalized circuit, and then transform the circuit in the second step, from the second step into the final circuit by using the transformation table. Okay, so if you have inductor in series, then for band stop filter, the inductor will be replaced by this structure. Okay, these components. Okay, let's look at an example. So a maximally flat low pass filter. So obviously this is Butterworth. Low pass filter is designed to have 40 dB attenuation. This is a stop band range at 4 GHz, the stop band frequency. So you know that the alpha S equal to 40 dB, and then the omega S 4 GHz. Sorry, this is Fs. So omega S is 2 pi Fs. So with characteristic impedance Z0 equal to 60 ohm, and a cutoff frequency, the omega C equal to 2 pi of Fc 1.5 gig, and with the attenuation of 3 dB. So this is the cutoff attenuation, right? So list all normalized element of low pass filter and sketch its normalized ladder circuit. So ladder circuit is the normalized circuit for that for this low pass filter. So normalized elements meaning that all the components involved in your circuit. Right, so as mentioned earlier, it will be good if you can represent this statement into a frequency response. Okay, so you can relate where is the cutoff frequency, where is the stop band frequency, the stop band gain, and etc. Right, so next, the second one, from the obtained answer in 1, so you'll be using whatever configuration you have in 1 to design a high pass filter with requirement of cutoff frequency for this high pass filter, omega c for high pass filter in this case equal to 6 GHz times 2 pi because it's omega. Alright, so then you need to include the ladder circuit, normalized circuit of the high pass filter, and also the actual one. Okay, let's proceed with the first step to determine the end. So the first, from the statement, it is stated as a low pass filter Butterworth. Alright, so maximally flat, low pass filter. So for low pass filter, to get the end, you need to know the omega Sn. So omega Sn by using graph. If you have the equation in hand, you can use the equation, or else you can refer to the graph, but you need to make sure that you use the correct equation for the omega Sn. In this case, low pass filter, so omega Sn at the bottom will be omega S divided by omega C minus 1. Okay. Alright, so once you have the omega Sn, so this is your omega Sn, okay, equal to 1.67. So 1.67 somewhere here, and then the stop band gain is 40, so the cross section is there. So in this case, obviously your n equal to 5. So next steps, once you have the n, so from earlier calculation or from the graph, n equal to 5, so refer to the circuit normalization table, so n equal to 5. So these are the components involved in your circuit, so n equal to 5, so the inductor and capacitor combination will be up to 5, and the last terminated with the load impedance, right? So for example, I'll be using the third configuration. Alright, so it begins with the inductor L1, so the value will be 0.618, and then followed by C2 1.61, L3 it's 2, and then C4. Okay, this is the from the figure earlier, but for this particular end, so you have the components up to 5, and then terminated with the load with value 1, are not normalized value equal to 1. So L1 in this case equal to 0.6180, and then 2 1.6180, and then 2 here is 1.6180 and 0.6180. Right, since we get the normalized circuit in hand. Alright, so next from the second question. Alright, so this is the second question. Don't forget, when you answer your test or exam, please make sure you write your question number in order with the question number. Okay, so please make sure you write down the sub-question number properly. Right, next, from the obtained answer in 1, design a high-pass filter with the cutoff frequency of omega c equal to 2 pi of 6 GHz. Okay, so you don't have, if the question asks you straight away to design a high-pass filter, then the omega Sn should consider the omega Sn for high pass filter. But since the question asks you to get the low pass filter component first in the first question, so the n is calculated based on the low pass filter, right? So then you for the second question, use whatever you have in 1. So you don't have to recalculate the N for high pass filter, okay, because the question asks you to straight away use whatever configuration you have in the second step and in the first question to get the high pass filter, meaning that you can use the normalized circuit from the question 1 to get your high pass filter transformation in this case. Alright, so this is from the question 1, sub question 1 normalized circuit. Alright, so then you need to reuse this to get the high pass filter as your final circuit. So you need to perform the filter transformation. So refer to the filter transformation table. So look at the component you have. For example, in this case, the first component. Okay, the first component you have in series is the inductor. So you have in the, okay, this is normalized circuit always in low pass filter mode. So you have the inductor in series. So in series inductor. So for high pass filter, this inductor will be transformed into a capacitor, right? So meaning that in the new circuit, this one will become a capacitor. And this is C1. And what is the C1 equation or value will be calculated based on this. It's 1 over omega C, the new omega C required. So in this case, 2 pi 6 gigahertz. L is the current normalized value. So L from L1 in this case, 0.618. Z0, the characteristic impedance given in the question is 60 ohm. Right, next, for the second component, you have the capacitor in parallel. In parallel, you have capacitor in this case. So you have capacitor. So to get a high pass filter, the capacitor will be transformed as an inductor. And what's the value for the inductor? It's Z0. Z0 is 60 divided by omega C is okay, the value 37.7 gig. Okay, I just put omega C here, and then C is the current normalized component, so it's 1.618, right? So you get the new or the actual value of the actual component, in this case the inductor. Okay, same goes to the other components. So this is the transformation, all right? So inductor becomes capacitor in the actual circuit. Next, the capacitor becomes inductor, and the third one, inductor in series again, becomes the capacitor, and so on. Okay, so then please make sure you calculate the actual value for each of the components involved, right? So don't forget to denormalize or get the actual value for the input impedance, also the load impedance as well. Okay, next, let's look at another example. So this question asks you to design a high pass filter lump element with 3 dB equal ripple. So obviously this is for Chevy Chef, right? A cutoff frequency of 3 gigahertz, so omega C equal to 2 pi of 3 gigahertz. At least 30 dB insertion loss at 2 gigahertz, right? So 30 dB insertion loss is the stop band value. So this is equal ripple high pass filter, all right? So high pass filter. Okay, and cutoff frequency at minus 3 dB. It is 2 pi 3 6 pi gig. Okay, this is your omega C, and then the stop band of 30 at 2. Here is your omega S, 2 pi 2 gig, right? So here is your 30 dB. Insertion loss or your stop band gain or attenuation. Alright, the characteristic impedance, so Z0 is given as 75 ohm. Okay. So the first step is to calculate the N. So to get the N, you need to know what is your omega Sn. So for high pass filter, so in this question, straight away the question asks you to design a high pass filter. Alright, so then you need to consider the omega Sn, normalized stop band frequency for the high pass filter. So in this case, the omega Sn equal to 0.5. Okay, next, refer to the graph. Okay, so omega Sn equal to 0.5. So here is your omega Sn equal to 0.5. Okay, and then the gain given is 30 dB. Okay, from the question. Alright, then you get your N in between 4 and 5. Obviously, you have to choose N equal to 5. Okay. Okay, next step, refer to the circuit normalization table. So N equal to 5. So you have all the components in hand. Alright, so you can choose the circuit configuration 1, 2, or 3. Okay, example, we use the configuration 1. Okay, width. Okay, here is your R0, the source. Okay, so here is your C1 or G1, L2, G2, and etc. Okay, so here is your G1, in this case is C1, so G2 in this case is L2. So you have 5, so the combination will be up to 5. So L2, C3, L4, and then C5. So up to capacitor C5, C3, C5, L4. Okay, and terminated with load resistance. Okay, normalized one. Okay, so once you have this, then to get the actual circuit, so step 3, you need to refer to the filter transformation table. So remember, the second step, always produce low pass filter normalized circuit. Then to convert this into high pass filter, so refer to the transformation. So the first one, you have the capacitor in parallel. So capacitor in parallel will becomes inductor, and the inductor will be transformed into a capacitor, and etc. Okay, so this is basically how the actual circuit looks like. So you need to calculate all the components values based on the actual equation. Okay, so then perform complete calculation. Then if you can include those values into the actual circuit, or you may label it as this and make sure you write the values properly with the unit, right, as your final circuit transformation. Okay, another example. So it will be a quick one. So since you have seen all the steps from earlier examples, so I'll be discussing this in brief. So design a band pass filter having 0.5 dB equal ripple. So when you have ripple, so it is a Chebyshev. So make sure you use the Chebyshev table and also Chebyshev graph with 0.5 dB equal ripple response. Then center frequency omega c equal to 2 pi 1 gig, and 10% bandwidth. So 10% bandwidth is the fractional bandwidth, right? So fractional bandwidth in the passband area is 10% or 0.1, and the attenuation of at least 30 dB at 1.25. So this is your omega s, okay, equal to 2 pi of 1.25 gig. the line impedance Z0 equal to 50 ohm. Okay, so as usual, the first step is to calculate the N. So to get the N from the graph, you need to have the omega Sn. So get the omega Sn for the band pass filter. So in band pass filter omega Sn calculation, you need to consider the fractional bandwidth value. So in this case, it's given as 0.1. Then the rest are the omega S. So you have the omega S and also the omega naught. Okay, so you have omega naught is the center frequency. This is the center frequency, omega naught. It is not the cutoff frequency. Okay, the center frequency, for example, this is band pass filter. So this is the center frequency, omega naught. Okay, not the cutoff. The cutoff is at minus 3 dB. Okay. For band pass filter, you have two cutoff frequency, omega C1, omega C2, and omega C1. Okay, so once you have the omega Sn, then you can refer to the equal ripple, the Chebyshev 0.5 dB graph. Okay, attenuation graph. So here is your omega Sn in the x-axis equal to 3.5. So then you'll get the N values from the graph. So the attenuation is 30 dB, and here is 3.5, here is 4, so 3.5 is somewhere in the middle. So this is the cross section. So get the higher N number, so in this case N equal to 3. So next step, as usual, get the low pass filter circuit, normalized circuit. Okay, normalized circuit, make sure you refer to the correct table, 0.5 ripple factor, Chebyshev, and then in this case N equal to 3. Okay, get the components, consider which configuration you want for the normalized circuit. For example, I'll be using this configuration, the third one. Then get your normalized circuit orientation, okay, or configuration. So N equal to 3, so the last component will be 3. So in this case, L3. So get the values into the normalized circuit. And lastly, terminated with the normalized load impedance equal to 1. Right, so once you have the normalized circuit, as usual, the third step will be the filter transformation from step 2, normalized circuit, into the required type of circuit of filter. Okay, next, once you have the low pass filter normalized circuit in step 2, so this is in low pass filter normalized circuit. So then transform the circuit into the actual one by using the transformation table. So in this case, from low pass to band pass, so the first component you have the inductor. So in the inductor will become a series of inductor and capacitor in series. Right, so the value for each of these should be calculated by using the following equations. And next, the second component, you have the parallel capacitor. It will be transformed into a parallel capacitor and inductor. So this one will become a parallel capacitor and also inductor. Okay, followed by the next component. So this is how your filter circuit looks like. Okay, let's mirror this. Okay, so then don't forget to calculate the actual value or the final value for each of the new component, right? So by using the equation shown in the transformation table, so then you get your final circuit or element values. Alright, from this slide onwards, there's more example on the filter design, so you can try this out. I'll not discuss this in details. Alright, so repeat the 3 steps, and in this case, in the question, there's additional question to plot your filter transformation, filter response. So obviously, if it is low pass filter, okay, just attenuation graph, we'll see something like this, the S21. So if it is the combination of the S21 and also the S11, so the S11 is the other side, okay, the other side of the S21. So however, the most important point here is the intersection between the S21, the attenuation graph, to the S11, the reflection coefficient graph. So is basically representing your omega c, the cutoff frequency at minus 3 dB. Okay, this represents the cutoff frequency in this case is 500 megahertz. Okay, so besides using the graph S11 graph and also the S21 graph as shown earlier, so you can also present the scattering parameter of a filter, for example S11 and S21, by using ABCD matrix, right? So you can analyze by using ABCD metric that you have seen in network analysis, right? In which of each of the components you have in the circuit may be represented with the ABCD matrix, and then multiplication between each of the matrix will produce output ABCD matrix. Then you can use ABCD values to calculate the S parameter. So for example, so example A, this is the output A, B, C, and D for this filter configuration. So the first one, you have Z0, so represents the first component ABCD matrix. So for series component, 1, Z0, 0, 1. All right, so this metric representation may be given to you during the test or exam. So, but for just basic structure or configuration, for example, in series, in parallel, you can just, I think you can just simply memorize that, right? And the second component here, okay, another Z in parallel. So for parallel component, you have its Y 1, 0, Y 1. So in this case, its capacitor Z equal to 1 over J omega C. So if Y, it is equal to J omega C. So next you have another component in series, inductor. So for series component, it's 1 Z01. So 1 Z01. So in this case, your Z is equal to J omega L. And then lastly, you have another component in parallel. So it's 1 Y again 0, 1. So in this case, it is ZL. So 1 over ZL 0, 1. Okay, so this is for this configuration. All right, and then you can expand this matrix until you get the ABCD. So this represents your A, here is your B, and then C and D. Okay, so once you have A, B, and C and D, then you can calculate what is your S11 and also S21 for the filter. Okay, so you have another example in here for bandpass filter. Okay, until you get the circuit realization, and also when you plot the S11 and also S21 to cross section, in which you have the two cutoff frequency for bandpass filter in this case. Right, so and another one, an example on bandstop filter. Okay, so I hope you try this out. So to make sure that you understand how to design the filter circuit, okay, depending on types of filter, And once you have the filter circuit, then you can use the simulator to simulate the design, and also finally, if everything is okay, then you can fabricate that for measurement purpose. Thank you.